had a logical error. So that gets multiplied, and it's summed over all the possible mechanisms, which is epsilon, of having that error. And we can then plot it. So if this is the inserted error probability and this is the logical error that you get, so without any intrinsic error in your system, that is like C0 gates and everything are perfect, then you get this line over here where if you have a higher probability of the inserted error, the logical error starts suffering. If you had a single physical qubit and no logical qubit, so a single ion is a single qubit of information, then this is how the logical qubit, logical error would scale with the inserted error probability. The non-fault tolerant qubit is actually worse than that because you have many C0 gates, and all of these C0 gates have error channels that bleed into the non-fault tolerant qubit. So they exhibit a higher logical error probability. The dotted line is simulation, the continuous line is experiments. But the fault tolerant qubit shows an improvement over the physical as well as the non-fault tolerant qubit by almost an order of magnitude. So this plateau over here where the inserted error probability, as you vary it, you stay fault tolerant in that logical qubit is kind of important, and that is the robustness that people will be talking about when they talk about quantum error detection. All right, so that was that, and maybe I will quickly try to go over this other results that we had in the system, in our processor. And here we were trying to do a Hubbard system try to simulate a Hubbard system of bosons in our system. And so basically going into the nuts and bolts of that, let's say you have 3 ions in your system with a certain separation. So the boson model will be implemented by choosing the local phonon modes of these ions. So what do I mean by that? So these ions are charged particles, and if I like kick this ion in the transverse direction, the other ion will feel that because the distance changes and you have Coulomb interaction. But if I look at very small time scales, then this guy will move and these guys will not respond yet, right? So that is called the local motion of this ion. So with all the other ions pinned, this ion sees a local harmonic potential, which will have local phonon modes, and this applies to all the ions. And in the regime where you're looking at it very quickly, you could excite these local phonon modes without the other ions knowing. Now, if you were to then wait for some time, these local phonon excitations would then hop coherently to the neighboring sites via the Coulomb interactions, and that gives rise to this sort of a phonon hopping Hamiltonian, where you have the local mode energy and then the hopping term in there. Now, everything happens here at time scales which is much, much faster than all the gates that we were doing previously. So, yeah.
So you're saying that if you put the phonon in one of the ions, that excitation just hops to one of the other ions?
Yeah.
But what term in the Hamiltonian tells me that such a process exists here?
Okay. So this is the hopping term in the Hamiltonian, but the way you you get that is that you can write the energies based on the displacement of the ions. So if you were to, for example, just write this displacement as A plus A dagger of each of these ions, then the energies could be decomposed. Then the energy can be approximated to the first order in A and A dagger. And the first order approximation of that energy that is displacement dependent of each of these ions gives you this hopping term.
Interaction is purely true.
Yes.
Now it's sort of flipping the whole problem, right? Here your excitations are now the phonon modes, not the spin of the
Yes.
That's the thing you're studying now.
Yes. So now I'm, yeah.
And then where does the K13 come from? I mean, you just have 3 ions, right?
K13, kappa 13. So that is the hopping term. So the hopping term is strongest with nearest neighboring, and then with the next nearest neighbor, it's like almost 1/8, like one. It goes as distance cubed. So it is weak, but it's still there. So essentially, basically, this ion having a vibration is going to be felt by this ion, and is going to be felt almost 8 times weaker by this ion. but it'll be there nonetheless because Coulomb interaction is long range.
The harmonic mode frequencies of all the ions are assumed to be identical.
No, they are not assumed to be identical. We will experimentally find out what these local mode frequencies are. So when we do ion chains and quantum gates using those ion chains, we look at the normal modes of motion. So all the ions are moving in sync, and but here we kick the ions so fast that the ion only, we only excite the local modes of these ions. And that's how we find out like what these local mode energies are. I'm going to show that. Yeah. All of these frequencies are near 3 megahertz. But then there is a little difference because these ions are not in the same spot. So they have a position dependent local mode frequency. For example, this ion,
You basically want to try to look at the response at rates faster than kappa.
yes, yeah. So the time scales of the experiment is much smaller than the inverse of the hopping rate. The time scales of the excitation, sorry. Yeah, time scale of
Evolution is on that. You want the
yeah,
hopping
yeah. I want the hopping to happen, but I want to.
The external motivation is the kicks are
Yeah. So for kicking it and for measuring its local phonon occupancy or phonon state, I do that much faster than the hopping rate. Okay. So in the setup, nothing has changed except for instead of 5 ions, I have 3 ions. Because each ion, I'm going to drive the sidebands transition on the local phonon modes of each ion. Hence, each ion is supposed to see a different Raman beat note. So I do that by modulating in these individual addressing beams with a multi-channel AWG, and that is the difference between this setup and the previous setup. And then I can just like increase or decrease the number of phonons by driving the red and the blue sidebands, but you have to remember that these phonon modes are now the local modes, not the normal modes on each ion. Okay. So I have the usual hopping Hamiltonian. So what I can do is I can go ahead and do a sideband spectroscopy, find out the local modes. So I increase my laser power and do a sideband pi pulse, which is much faster than the hopping rate. And I find that for each ion, I get exactly 2 modes. If there were 3 ions and normal, there will be 3 normal modes. But if you are looking at the local modes, then there will be 2 modes because in the I'm kicking it in the transverse direction, and then there are 2 orthogonal degrees of freedom in the transverse directions. So that tells me that I am successfully preparing or exciting local phonon modes. Now, in an experiment, what we do is we sideband cool each of these ions to the ground state of the local phonon mode. Then we initialize, we put 1 phonon occupancy in, let's say, the middle ion here using a blue sideband pi pulse and a carrier pi pulse. So that just introduces 1 phonon here. And then we wait for some time for it to hop back and forth between the other ions. And then in the end, we measure a single phonon occupancy by doing a red sideband pi pulse. So this red sideband pi pulse maps the phonon occupancy 0 or 1 to the spin state 0 or 1. And then we can measure the spin state with high efficiency. But there is something else that is going on here. What we have done is we have introduced a perturbation. This is a Jaynes-Cumming interaction, where we are so strongly driving the ion 3 here in this case that I have created a spin and local phonon rest state which has energy splittings which are much larger than the local phonon energies. So what that does is it creates a blockade and prevents hopping of phonon from this ion to this ion. So we are not only studying the hopping, the free hopping of local phonons, but also introducing blockade in the system. Sort of what you expect in a Bose-Hubbard model where you have hopping and blockade at the same time. Okay, so here are the results. First, I do free hopping. The shaded ones show which ions.
How can you, these are electrostatic frequencies which are not, how do you know that you're only doing it for ion 3 and not for others? Like, I mean, because you could have these are electrostatic controls.
No, this is using Raman beams. So I have a focused Raman beam on ion 3 that drives it. Yeah. So I have selectivity of addressing each one of those local modes by actually like using the focused laser beam that is going to hit that ion. And at the same time, I can tune the frequency of each one of these Raman beams. So that frequency can be arbitrarily tuned to address each one of these local modes, even if they're not the same.
But the trap strength itself in which these modes, local modes are, that you can tune electrostatically. Is that correct? Or
Yes, yes, but when I do that, then all these local modes move together almost, more or less, yeah. Yeah, so in this case, so here's the result. First, free hopping, right? So the first or the second or the third ion has a phonon in it. Then that phonon coherently hops to the next one, and I see these oscillations over time. So I introduce this excitation, I let it hop, and then I very quickly measure it by mapping the phonon state to the spin state, and then doing my standard fluorescence detection. If the phonon is in the middle ion, then it hops to either. If it's on the right ion, then it hops mostly to the middle one. So there is asymmetry. All of these don't look very nice, like very symmetric. They're nice, but they're not very symmetric. And the reason is, this is how we find out that in our ion trap, the local phonon modes, which are supposed to have symmetric energies, because there should be left-right symmetry if the ion trap has left-right symmetry, it does not. So the relative energy between the local phonon modes is such that this one is higher than the next one, then it is higher than the next one, right? Which gives rise to that. Yeah, so they would completely exchange if this was right next to each other, but it is not. So it's like a partial beam splitter. It's like not 50-50. All right. Okay, so we see the free hopping, and that tells us what the local mode energies look like. Then I can suppress that hopping. So just to correspond the free hopping with the suppressed or the blockaded picture, with excitations on 1, 2, and 3, I put a blockade on the nearest neighboring ion. For example, this guy, I put a blockade on the third ion. It is suppressed. Hopping continues between the first two. If I put a blockade on the first ion, hopping continues between the next two. The first one goes down. And because
what, guides to ion or fits? It's kind of confusing. Dots are data.
Dots are data. The lines are fits.
Are fits.
Yeah. Okay. So there is a simulation and then there is a fit. Yeah. So the simulation assumes. So there are other calibrations that we do in order to find out how purely we prepared the phonon states, local phonon states, and we take that into account into the simulation to tell us what sort of hopping we should see. And these are the plots. So that's the first stage, and then we keep a few variables. So it's kind of both. Yeah.
Because I guess for the prediction, you need parameters from the experiment.
Yeah. Yeah. So there are parameters that keep changing between the different experimental runs. So that's why they are floating. So from this sort of like simulation fits, we get the blockade strengths, which are nothing but the proportional to the red sideband Rabi frequency. And if we directly measure the red sideband Rabi frequency by doing the red sideband spectroscopy on the local modes, then they sort of match within 10% of what we get here. All right, and that's that. So this is my concluding slide. It's an outlook of where this trapped ion quantum computing system is going. There are and all of these are with intent to scale up the system. So the possible directions to go is that you can have separate processors which are connected photonically, which do heralded entanglement, and that is how you can scale up the system. There is this other architecture which is called the quantum charge coupled device, where you have multi-zone ion traps, and you can actually shuttle these ions around to connect different zones, because one zone with a few number of ions is more manageable than having a lot of ions in a single zone. And this is sort of a prototype that is being built by a company in Maryland now. It is the next stage of this quantum processor. It's an integrated system. It's going to be about half a meter in size, and it's going to have a different kind of a chip. So the kind of hand assembled trap that we used, which had this sort of inharmonicity in the trapping parameters, those things will not be an issue with these surface fabricated chips. And with that, I would like.
This is a commercially available trap now?
This no.
You said some company is making.
So IonQ is making it in Maryland, yes. Sir. Yeah. This is anyways, so these are the people who have been working in the experiment. Chris Monroe, my advisor, my lab mates, and my previous lab mates who worked on the pulse shaping scheme. And we have collaborations with Looming Duan's group from University of Michigan, who helps us find out the theory behind this phonon hopping and these pulse shaping schemes. So thank you for your attention.
The last question for maybe other quick questions. Okay, all right.
Anyways.
Thank you.